Section 9.6, the ratio and roots test. All right. The ratio test is going to be one of your go-to tests. Root test, not so much. All right. So A sub n is a series of non-zero terms. And what we're going to look at is the ratio between each successive term. So this will be the nth term, this will be the n plus 1 term, or the next term. All right. And we're looking at the ratio, and the ratio must be in this order, right? The next term has to be above the previous term, right? And if that limit is less than 1, then it converges, absolutely. If it's greater than 1 or infinity, it diverges. And if it's equal to 1, then the test is inconclusive. All right, so let's just look at this. You'll notice in the first example, we have n factorial. What you will find is that this test is very good for problems that have factorials in it, right? Because they cancel nicely. All right, so first, the real setup looks like this. Limit as n goes to infinity, a sub n plus 1. So plug in n plus 1 into n, so it's 2 to the n plus 1 over n plus 1 factorial over, and then the previous value, which would be 2 to the n over n factorial. Now that's and it's absolute value, but you will notice that 2 to the n is never negative, and neither is n factorial. So that's all positive, so I don't need the absolute value symbols. All right, then we're going to do a little bit of algebra. So that's going to be 2 to the n plus 1 over n plus 1 factorial times, and then remember, whenever you have fractions like this, or division, think of this as division, you're doing the first top fraction divided by the bottom fraction. You multiply and take the reciprocal of the bottom fraction, so it's n factorial over 2 to the n. Okay, so I'm going to drag this out a little bit, drag out the algebra, so it's easier to digest. So I'm going to swap these two so they look easier to cancel. You can do that because multiplication is commutative. That's an n, not an m. Okay, so 2 to the n plus 1 over 2 to the n, that cancels, right? You subtract the exponents. So that's going to be 2 to the 1 in the numerator. And then n factorial over n plus 1 factorial. So remember, n plus 1 factorial, so this is just side note, n plus 1 factorial is equal to n plus 1 times, and you subtract 1, so that's n factorial. So it's n plus 1 factorial is n plus 1 times n factorial. So this is going to cancel, leaving you just n plus 1. All right? So the limit of this as n goes to infinity is 0. So this converges absolutely. All right. That's example A. Example B. Do the same thing, except I want to skip this step. I want to go ahead and go straight to the second step. All right, I'm going to go straight to the second step. Just to note here, there's no chance of any of this turning negative because we're plugging in positive values for m, so this is all positive. All right, so let's go straight to the second step. So plus the n plus 1 first, so it's n plus 1 squared, 2 to the n plus 2, because it's n plus 1, over 3 to the n plus 1, times the reciprocal, so that's going to be 3 to the n, over n squared, and 2 to the n plus 1. Let's do some algebra here. So I'm just going to write the n plus 1 squared over n squared. So it's n plus 1 squared over n squared. And then this part here, 3n and 3n plus 1, it's going to leave you a 3 in the denominator, right? 3n basically subtracts. Here, 2n plus 2 divided by n plus 1, it's going to leave you 2 in the numerator. And the limit of that is 2/3. Right, this part limit is 1 because it's basically a quadratic over quadratic, so just left with the 2/3. All right, so it is less than 1, right? The requirement is for the limit to be less than 1. So this one converges absolutely. All right, E. Again, set up my limit. That will be n plus 1 to the n plus 1 over n plus 1 factorial. Multiply that by the reciprocal of that term. Okay, do some algebra. So we'll swap these two. Okay, so these two reduce to, so that's over n plus 1. So what I have is, now I'm going to do something weird, n plus 1 to the n times n plus 1, right? So what I've done is write this numerator as this, right? The n plus 1 means there's n, and then there's a n plus 1 to the first power. This reduces to n plus 1, and I'm not doing anything with that. Just copying that. So these reduce again. So what I have now is the limit as n goes to infinity of n plus 1 to the n over n to the n. Okay, now what you may not know is that this is equivalent to n to the infinity n plus 1 over n to the n, right? If you have the same exponent, you can rewrite it like that. And this is similar to, or exactly the same as, not just similar. All right, 1 plus 1 over n to the n. This has a limit of e. This is greater than 1, so this diverges. Okay, all right, remember if it's bigger than 1 or infinity, it diverges. And this is e, which is 2.7, so it's bigger than 1, so it diverges. And then this one, it's an alternating series, so you wouldn't use the ratio test. And in fact, let's see what happens when you do the ratio test, though, just for kicks. So it's going to be a limit as n goes to infinity. So remember, we're taking the absolute value, so the negative 1 goes away. Square root n plus 1 over n plus 2 times the reciprocal n plus 1 over square root of n. And if you look at that, they're basically the same numerator and denominator, so the limit is 1, and it's inconclusive. But this is an alternating series, so you should just use the alternating series test. And this would converge based on the alternating series test. All right, next page, or we could just stop it there. Let's stop it there.